it visible to all?
Yes, sir.
Yes, sir.
Yeah. So last time I have discussed Gauss radial basis function and 3-point compact discretization for non-linear second order differential equation. And we have also seen the graph of radial basis function by choosing different values of x naught. You have seen that the graph moves left or center or right depending on that. So now I am going to present a Python algorithm for the linear problem and for the non-linear problem. The writing style is exactly same as, but to start with, I have started with linear problem. Our equation is d2u, the most general form of linear equation in second order. It is d2u by dx square is equal to a of u derivative plus b of b into u plus function g. So this is the example what I have given in the slide. So this is what I have written has. This is something like a comment line in Python, and Python is Python is having very rich tools of mathematical functions, solver. So many things are given here as compared to C or Fortran or Java. We have a rich library. That is why mathematician or computer scientists nowadays prefer to use Python. So I'm going to use so many modules here. So this is what the actual programming starts from this line: import numpy. Import numpy, I will write numpy in the short form as NP. Even if any of you are not aware of the programming, they can simply understand it, how we are using it for solving mathematical problems. So numpy is a library in which we are doing numerical calculation. So it is just like our kitchen in our house is a module in which we are cooking food. So we in this programming, we are having different types of module. NumPy is one of a module in which we are doing numerical calculation. Thereafter, import matplotlib. This is basically for the plotting of the function. Thereafter, I will use from NumPy, I will use linear algebra package. So this is what lin ALG, linear algebra package. So this I will denote in the short as LA. Thereafter, I will import math. Import math is used to import sine, cos, tan, exp, all those kind of things. Not only from math, I am going to import everything. This is what a star denoted by a star, and array. I am going to use array. So that will be again used by the symbol import a star. Now, in our differential equation involves the function a, b, and g. Our differential equation is, I'm just telling you, I'm sending it on the WhatsApp. It is d2u by dx squared. Just a moment. So I have seen the problem which I have coded here. It is ax, bx, and gx are three functions of x which is known to us beforehand. So I have to define all these kind of things. So this is what I have defined by writing def, def ax colon return x. This is a syntax of defining a function ax is equal to x. Ax is equal to x in mathematics is written as def ax colon return x. Similarly, bx, I am going to take 1, and exact u is the solution which I have taken here to show you what is the error in the solution. The error of the solution will tell you whether we are moving in a right direction or wrong direction. This is for testing purpose. So exact u is given, and if exact u is given, you can find gx here in the programming I have written uppercase G. Now our radial basis function involves a parameter c, so for that c you have to choose some value. I have taken here c equal to 1. It can change while at the time of simulation you can change this value. Here although I have taken LL stands for total number of grid points that I am going to take. Actually the total number of grid points is LL plus 2. Why? Because we have one two for the boundary points. Uppercase LL is here written as lowercase ll. That is the internal number of grid points. So I have used these two lines, just don't mind for the time being, and because I have taken it in the loop just to run it so many times. But for the understanding point of view, just you take C is 1, N is 1, N is used for generation of grid. And here I have taken LL is equal to 10, 20, 40, and 80. That is, I will first of all for LL equal to 10 means I am going to calculate solution error, L infinity error and L2 error for 10 number of internal grid points. Then I will calculate 20 number of internal grid points and then compare the solution. Similarly for 40, similarly for 80, and so on. Now I have defined x as a np dot zeros. X is a vector which consists of LL plus 2 number of that is, it is something like x0, x1, x2, xll plus 2. Each of them initially consists of value 0. This is used for the grid. S is also used for grid. U is the solution which I am going to calculate. Here I have taken initial solution is 0. These are the array that is going to used in calculating in applying Thomas algorithm. Old U, OU, and UU. Well, UU is required for the non-linear because the heading of the program for the linear or non-linear is kept as same. That is why I kept it here. Thereafter, most important is sub, DG, sup, and RH. Sub is the sub diagonal, DG is the main diagonal, and sup is the super diagonal, and RH is the right hand side vector. I have written here IM, that is of no use for you, but this is two-dimensional. This is LL comma LL, two-dimensional vector which initially consists of 0, 0. I have used it here to determine the condition number of the matrix, because please recall in the radial basis function I have told you that one has to avoid singular computation. That is why polynomial is added in the radial basis function. So you have to see what is the condition number of the matrix. That is also one of a parameter to measure what is the condition number of the algorithm. If the condition number is very high, exceptionally high, then that is comparatively not regarded as good algorithm. Now here I have taken the domain xa equal to -4 and xb equal to 4. That is, our left end it as -4 and right end is at 4. So -4 to 4 is divided initially at 10 number of points, thereafter 20, and so on. And here h is basically defined as xb minus xa by LLD plus 1. LLD is exactly same as LL. Why I have this is my habit of writing. LL is assigned in LLD. This is what in here written, LLD equal to LL. This is actually my habit of writing C++ program. In C++, actually division by integer gives you the integer result. So better you have to assign it in a float or double precision number. But in the Python, this problem is not there, but my habit continues. That is why I have written LLD equal to LL. But for you, keep it, both are one and the same thing. Mathematically also here assigned. And H is the step size. So here for L in the range 0 to LL plus 2, so range is a command that will assign value from 0 to LL plus 2, but LL plus 2 is excluded. So you will get points 0 to LL plus 1 only. The last point in the range is last number is not calculated. So we will get x0, x1, x2 up to xll plus 1. So by this way, I have got the grid here, right? Now, I have printed all these grid, although I have kept it in the comment line, but you can, by removing the comment, you can print these grids. Now, this is U0. U0 is the value of U at x0. The value of U at x0 is known to us from the boundary values, that is uppercase A in the slide I have written. And U at the last point is given as uppercase B. So uppercase A is, I have calculated it from the exact solution, exact U x naught. And U at the last point, ULL plus 1 is basically.
रोज का इतना ही करो, रोज भी अगर ट्यूशन पढ़ते हैं, रोज भी नहीं होती, अगर रोज भी करते हो, 1 घंटा भी पढ़ोगे तो मुर्दा नहीं लगता.
It is exact.
Please mute yourself.
ये समझा देती हूँ यूक्लिड्स को, इसमें कुछ नहीं रटने, इस तरह समझने वाला, रीडिंग करना.
So now this is old U is assigned with 0 and UL is assigned with old U. This is required at the time of finding solution. Now, as I told you, you have to calculate U0, U1, U2. So this is what now I will calculate here U0, U1, U2. I told you I will write by manual writing, I will write U0, but U0 stands for UL. Similarly, U1 stands for U at x1, which is actually U at LL plus 1, XLL plus 1, XL plus 1. Similarly, U2 is U at x2, which is x2 is actually XL minus 1. So this is what, this is just the, because I am writing code in this way, that is why at the time of deriving, we are using similar kind of symbols. So at the time of writing code, we have less confusion. Now, this H is required. H is basically a step size, and P is again a parameter which is basically defined as next step size divided by previous step size. So this is, in this case, it is 1, but it can change. Now, we are having 3 functions, A, B, and G. So again, for A, I have calculated what is A0, A1, A2 in terms of L, L plus 1 and L minus 1. Similarly for B, similarly for G. Please note that everything is happening in the loop. L is going from 1 to LL plus 1. Again, it is range, so it will calculate, it will go up to 1, 2, 3 up to LL, that is uppercase L. Internal number of grid points will be calculated only, that's all. Now, you see what are the radial basis weight that I have to assign it here. Radial basis weights are assigned here. I have assigned it here in the loop. In fact, it is very much required to assign it in the loop if you are taking different values of LL. If you are calculating for only one values of LL, then there is no need to put it inside the loop. You can put it outside, but it is suggested to use it in the loop. So here, these are the mathematical values of all the weight, RBF weight. So I'm just scrolling down, all A's are here. So this part, before this, I have given the weight of RBF, that's all. Now, our job starts. What is subdiagonal? What is main diagonal? What is subdiagonal? So that you have to calculate. What is subdiagonal? Is the coefficient of U2 in the scheme. What is diagonal? Coefficient of U0. And what is sub? Coefficient of U1, that is UL plus 1. So these things I will calculate, and I have assigned it here. Sub L is this, DZL is this, and sub L is this. RHL is this. Whatever left after sub, DG and sub, subtract it from the scheme, you will get right hand side, put it in the right hand side. So I have got these three equations. I will tell you, these things are very easy. I will just wait some 10 minutes. You will see how easy these things are. Now, please recall, in the matrix, what I have shown in the slide, when lowercase l equal to 1, I am getting U0. So somehow this U0 part will go to the right hand side for the L equal to 1 and for L equal to LL. For the first point and for the last point. So I have to rearrange. This is what I have written. If L equal to 1, then RH is basically RHL minus sub L into U2. What is this U2? U2 is UL minus 1. So it is L minus 1. L is 1. So it is 1 minus 1. It is 0. It is U0. U0 is known to you beforehand. That is why I have done it like this. This is for Dirichlet boundary condition. Similarly, for L equal to LL, this here it is sub, here it is sub, is going to the right hand side. Now, before this line, I have formulated, I have made our matrix AU equal to B. Now AU equal to B is ready. Now simply I have to calculate U equal to A inverse B. Till this part, till this line, I have just formulated our matrix system. All right. Now what left? Now next job is just left is to find the inverse. Inverse of a matrix is done by tridiagonal solver or Gauss elimination method or Gauss-Jacobi method, Gauss-Seidel method. So many methods are already known to you at the bachelor's level. Just I am going to apply it here. This is basically this is the code for, you can say, Gauss elimination method or tridiagonal solver. So these 5 lines are just the code. These 5-6 lines of code are directly extended to the 2-dimensional elliptic equation, 3-dimensional elliptic equation, exactly on the same line of pattern, right? Even for the parabolic case, hyperbolic case, at each time level, one can utilize this kind of system if the boundary condition is of Dirichlet type, and this kind of matrix if you are getting. Now the question is here, till here, I have calculated using this solver, I have calculated the value of U. Now the solution of U is known to us at each grid points. Now the question is whether the solution that we have calculated is correct or not. That we have to measure. So there are some or 1 or 2 norms are very well-known norms. L infinity norms, L2 norms are known to us. We are going to implement it here. Initially, RMU is this is and MAU. These are the 2 variables. I have defined it here to assign error in it. So, and this ERU is again just a name of a variable in which I am going to write absolute value of UL minus exact UL. So this is basically norm of U minus exact U. because U is available to us at each grid point. So it is UL. So here it is mod of, it is in one dimension. So it is mod of UL minus exact UXL. So I have compared the solution UL, which I have calculated here, and exact solution, which is already known to us. And then I have assigned it to a variable whose name is ERU. Now, thereafter, RMU equal to RMU plus ERU square. This is ERU square. So here RMU is 0 at the first case. So it is RMU equal to 0 plus ERU square. And if MAU is less than ERU, ERU is assigned to MAU. So this is, there are two things I am calculating here. Number one, here if condition here will tell you the maximum absolute error. So this will basically give you L infinity error. MAU will give you L infinity error. And here in ERU, basically I have calculated mod of UL minus exact UL. And then I am going to, each time I am going to add. So it is something like mod of alpha 1 square plus, mod of alpha 1 square plus mod of alpha 2 square and so on up to plus mod of alpha n square. So L2 norm is basically a square root of this, square root of alpha 1 square plus alpha 2 square alpha n square. So this is what here in the last line I have calculated a square root of RMU, or of course divided by LLD. LLD is the total number of points, internal number of grid points. So this is how L infinity and L2 norm is written in two lines here. It's clear to you all? Is it okay? Well, I assume it is okay. Now I have to calculate order. So order in L infinity norm and order in L2 norm. So this is by the formula log base 2. So it is log of TMU by MAU. T is the new error and MAU is the old error. So I have calculated and just nothing to do. Simply I have printed the solution here. This is the print everything. Print I have printed LL. I have printed C. C is basically your shape parameter, and this is L infinity error. This is L2 error, and this is order of L infinity, and this is order of L2 error. And then I have plotted it, the solution what I have got. Actually, the plot I have shown it in the slide that time because this is again this plot file is another graph, so that needs to be included in the LaTeX file. So I have shown it in the LaTeX file. If you would like to see, I will show it once again. Now just see. This is the error and computational rate that I have got from this solution, this algorithm. Here in each case, I have taken C as 1. C can't be 0. C can't be 0, but it can tends to 0. So in case of C equal to 1, maximum absolute error is this 3.83 E plus 0. And for L equal to 20, the absolute error is 3.69 minus 1. E minus 1 stands for 10 raised to the power minus 1. Similarly, here E minus 0.2 stands for 10 raised to the power minus 2 and so on. So, but just see this column. Here I have seen the error is coming out to be from 0, minus 1, minus 2, minus 3. So error is decreasing as the number of points 10, 20, 40, 80, as the number of internal grid points are increasing, the L infinity error is decreasing. Now the question is, it is decreasing, but in what direction it is decreasing, in what magnitude it is decreasing? That is being measured by the help of order. So this is the order: 3.4, 3.8, 3.9. So I have told you, I have discussed fourth order method, and this is close to 4. 3.8, 3.9, 3.4, this is close to 4. So the order is close to 4. Right now, same way, similar, exactly same interpretation can be done for L2 error. This is what written in terms of RMU. This is L2 error, and here it is the order of L2 error. It is also coming out to be close to 4. Now, this is the calculation when shape parameter is taken out to be 1. Now, just observe what is the effect of shape parameter on the solution error. So here I have taken shape parameter C as 0.2. Everything remains same. Similarly, simply I have substituted C equal to 0.2 instead of 1. Then the error is coming out to be this line, this line, this line. My mouse pointer is visible to you all, I assume. This is the error. Now, same way we can interpret error, order, everything fine, but I would like to mention that just compare the error in case of shape parameter C equal to 1 and in case of shape parameter C equal to 0.2. Which one is better? Here it is 3.8 plus 0. Here 2.3 minus 1. So this is better. Similarly, here it is 3.6 minus 1. Here it is 1.8 minus 2. 2.6 minus 2. Here 1.25 minus 3. Here it is 1.8 minus 3. Here it is 8.4 minus 5. So this is giving less error compared to C equal to 1. So this, by comparing these two results, we can simply draw the conclusion that shape parameter affect the solution. And why not? You have seen by changing the value of C, the shape of the curve is changed. Rather, not only shape, in fact, the area under the curve is also changed. It does not like Dirac delta function kind of things. No, here the area is also changing. So shape parameter of radial basis function is affecting the solution error and consequently the solution. Now, listen. The question is why we are using this method, radial basis function. Here, shape parameter C is basically a tuning parameter kind of things that is in our hand, and we can tune it accordingly so that we can get better solution or the solution as per our expectation. If C is taken to be limit goes to 0, in case of direct discretization, C is taken out to be in the limiting case takes C equal to 0. You do not have any option in your hand so that you can tune the solution. Here this tuning parameter will help in determining, in measuring good solution. All right. Any question? So this is very important. There are other parameters also that can be helpful in tuning the solution, but here C is very helpful to us. Now I am coming to the non-linear problem, the celebrated equation, again, this Burger's equation, a stationary Burger's equation. Here I have defined remaining imports are all kind of same thing. Here some parameters are defined as this is the global, epsilon and lambda, and these are the definition of function exactly on the same line here. So there is nothing to discuss here for the same L. Here I have taken for C in 0.1, 2 and 3. So 3 values of shape parameters are taken, and you will see the result. Now exactly same as I will tell you where the difference in linear and non-linear appears here. So this is exactly same as nothing to discuss. Here again the formation of grid. Here again initial condition U0 and ULL plus 1. Now actual change appears from this line. Actual change appears from this line. Listen, all of you are aware of Newton-Raphson method. Very interesting. I like this method by core of my heart. And I tell you, well, this method is very old, but it is such a wonderful and powerful method that it will give you solution in a fraction of second, because it has very less number of calculation. If you recall Newton-Raphson method, it is simply saying xk plus 1 equal to xk minus f by f derivative. F is the function, fx is equal to 0, whose roots you are going to calculate. So here f at xk and divided by f derivative at xk. Now, so what are the operation that we are doing? One of them is I am dividing f by f derivative. This is one operation, division, and the another operation is xk minus of this. So 2 operations. Computationally, only 2 operations are happening. Well, other operations are also there. Suppose your function is x square plus 2x plus 9. So 3 operations are there. That is different aspect. But here in the formula, I have only 3 mathematical calculations appears. That is why it is very fast. So, and it is in the formula, it is xk plus 1. It is the iterative method. So you take value of k equal to 0, you will get x1, then take value of k equal to 1, you will get x2. So you are going to put it basically in a loop. So here also exactly same thing I am going to do it here. Here I am going to put it in the loop. That loop is for kk in the range 1 to 99. I do not know in how many iterations it will convert. So I have taken up to 999. Let us see. I will see in how many iterations it will convert. At that point, I will stop. So thereafter, exactly same thing. L is taken in the range 1 to LL plus 1. And here H U0, U1, U2 is defined. All these weights are exactly same line here. Same line, not same line, rather exactly same weights are also here. So I am going to move to this step. Now here it is sub L. I have to calculate sub diagonal and super diagonal. Now in the linear case, I have calculated sub diagonal by finding coefficient of U2. Here it is a non-linear problem. We cannot find coefficient. So what to do? We will basically find del f by del U2. We can find partial derivative. So this sub L is nothing but, if I denote whole scheme by uppercase T, then this is nothing but sub L is basically del uppercase T by del U2. Similarly, dz is calculated, dzl is calculated by the help of del t by del u naught, Jacobian. And again, soup is basically del t by del uppercase t by del u1. All sub dg soup is calculated. Now you have to write what is RH. This F3 is basically RH. In the last here I have written RHL equal to F3. What is this RH? RH is basically your whole of the scheme. Whole uppercase T is your RH. And then use same tridiagonal solver, but with the U defined newly. So I will calculate same solver is here, but instead of U, I have a new vector that is UU. So UU is calculated. And Newton-Raphson method is saying U equal to UL plus ULN. Here I have calculated, this is basically F by del F. Listen. Your Newton-Raphson formula, xk plus 1 equal to xk plus F by F derivative. Here it is UULL is basically F by F derivative. And here it is UL equal to UL plus. That's all. Now UL is known to you. Now the solution U is known to you because it was in the iteration. So I have to add it. Now the question is, I have started KK from 1 to 99. The question is, at what step we have to stop? So that needs to be analyzed as follows. So I will calculate first of all error. So here it is also L infinity error and L2 error is calculated exactly same way the way we calculated for the linear problem. Now here this will tell you whether you have to, at which place you have to stop. So I will calculate, I will just write big is equal to 0 and I will calculate FU equal to absolute of UL minus old UL. The new value of U I have got and old value of U that available to us previously. I will find the difference between them. And if this difference is less than FU, if big is less than FU is assigned to big. And if big is less than 10 raised to the power minus 10, I have to stop. This is what I have written, break. So if the difference between two consecutive iterations, the difference of solution in two consecutive iteration is less than 10 raised to the power minus 10, I will stop. I am satisfied with the difference of 10 raised to the power minus 10. You can go up to 10 raised to the power minus 12, 13, 14, but I would like to mention that in C or C++, putting 10 raised to the power minus 15 till minus 15 is fine, but beyond that it has of it does not give you satisfactory result. In Python also similar kind of things happening, but at the same time I am telling you 10 raised to the power minus 10 and 10 raised to the power minus 13, 14 is very beautiful accuracy. So I have to stop. This is basically called error tolerance. Error tolerance is here 10 raised to the power minus 10. Now I will assign each UL in old UL and this loop continues. Here this will calculate order, and this here by printing this I have printed everything, LL, N, C, KK, everything, and here I have got the result. So for C equal to 0.1, I am getting this 9 minus 4, 7.11 minus 5, 4.9 minus 6, 3.2 minus 7. Here for C equal to 2, here it is this minus 3, 4, 5, 7. Here C equal to 3, minus 3, 4, 5, 6, and so on. So here also, in this case also, I have seen that when C is less, C is 0.1, this is giving better result, right? This is just by chance. It may be possible that for C equal to 5, you can get good result compared to C equal to 0.1. It depends on the problem. The problem what I have considered here is a regular problem, right? In the Burgers equation, I have taken Reynolds number equal to 1. Fine. Reynolds number 1 is not a big problem, but when you take Reynolds number equal to 50,000, you have to tune C in such a way that you get satisfactory result. In that case, a small c will not work at all. So this is all about the Python calculation. I would like to add one more thing. Why I have taken number of grid points coming to the first line. Here in the calculation, I have taken LL equal to 10, 20, 40, 80. Please note that I have taken internal number of grid points as twice, 10 to the 20, 20 to the 40, 40 to the 80, two times. And here at the time of calculating error, with base 2, twice of that LL. If you take thrice, 10, 30, 90 and so on, then you have to take log 3. But usually in one-dimensional problem, taking 100 grids is fine, you can work with. But if you move to two-dimension problem, this 100 grid will become 100 multiplied by 100. So 100 into 100 number of grids is it is very time consuming. That is why usually we used to stop here at 10, 20, 40, 80 like this. So this is the relationship with taking log 2 in connection with the number of internal grid points that we have chosen earlier. This is I will share this programming code and then yes, any question, any doubt?
No, sir.
Okay. So I am moving to the next topic. If you wish, you can take 2 minutes of breath. Let me share this slide.
Okay, sir.
Okay. Yeah. So now there is another topic. Actually, whatever I have discussed is for Gauss radial basis function. There are other types of radial basis function also. So I am going to discuss with this with inverse quadratic radial basis function. This is another type of radial basis function, very interesting. So let me start, and probably if time permits tomorrow, then I will move to the 2 dimension, and then we'll tell you what is this happening basically in 2 dimension. Here, instead of Gauss radial basis function, I am going to discuss another category that is called inverse quadratic radial basis function. So On the same line, I will have second order inverse quadratic radial basis function, fourth order inverse quadratic radial basis function, and we'll apply it for two types of problem, linear and non-linear. Now, what is this inverse quadratic radial basis function? Here psi is basically defined as, here r, psi r equal to 1 by 1 plus c square x minus xj mod square. So this is x minus xj is basically mod. Mod is basically r. R is basically distance of x minus xj. So here c is again belongs to real number, is a shape parameter. I forget to write c is positive, so please note that this is here c is positive. Now our domain is omega a to b, partitioned like this, x I is going from 1 to I plus 1, and xi is here it is basically 0. Is 52. Is I equal to 0 to I plus 1. I will correct it and then I will send. So here it is xi equal to a plus ih. I is going from 0 to ll plus 1, or you take I plus 1. L, uppercase L and uppercase I are one and the same quantity. Now, at the point x equal to xi, again I will denote ui as u at xi be the exact solution, and this is the problem. Uxx stands for double derivative of u with respect to x and equal to function of x, u and ux with the boundary condition, Dirichlet boundary condition. We will construct 3-point approximation like this. Our notations are exactly on the same line. U0 is at u at xi, u1 is u at xi plus h, and u2 equal to xi minus h. Again, in the subsequent derivation, exactly on the same line, I will use x0, x1 and x2 as the points appearing right hand side and left hand side. So here inverse quadratic function is defined like this: r naught x equal to 1 by 1 plus c square x minus x naught square. On the same line, I will define r1 x and r2 x. So 3 radial basis function, same line of pattern I have defined like this. Now, as discussed previously, here I will consider linear combination. Here I will consider linear combination, and r naught prime, this is first derivative, r1 prime second line, and r2 prime. This will give you the approximation of first derivative by using the values of weights obtained from this matrix. And you can check if c is not equal to 0, this coefficient matrix is non-singular. So from here, I am going to move little faster because it is exactly on the same line. The only thing is RBF is different. So here I will calculate A00, A01, A02. I got it like this. So here in this linear combination, this is our linear combination equation. Here A00, here A00, U0. Here again A01 R0 X1, so here A01 U1, and A02 R0 X2, so here it is A02 U2. Got the approximation at X0. This is also second order approximation of first derivative. Exactly on the same line, I will calculate x approximation at x equal to x1. So this is what, by forming this kind of linear combination, I will have this. This is the matrix. Find the weight. This is the weight. And as a result, you will get this approximation at x1. Similarly, at x equal to x2, we are having this matrix system, and we get these values, and this is the approximation. Now again, what left? we need to calculate the second derivative approximation. So here it is, this is for second derivative. Here R not single prime is written, it is basically double prime. Let me write, I will correct it and then I will send you the slide, page 58. It is basically R0 double prime. Yeah. So this is basically, please take it as double prime. This double prime is related by this linear combination. Solve it at x equal to x naught. You will have three linear equation can be solved for. Here also it is, please note that here it is A30, A31, A32. Here it is A30, A31, A32. Here this value is written correctly. You will get this one. So this is again coming out to be second order approximation. Now you can verify by the help of series expansion that the difference of u bar prime minus u prime at x0 is coming out to be this 2c square h square u0 prime plus h square u0 triple prime plus order h4. So this is basically, this right hand side is actually coming out to be order h square. Same thing will happen at x1, same thing will happen at x2, and for the second derivative it is also h square. And interestingly, as I have said previous, in the Gauss, if I take limit c goes to 0, what is happening? This is nothing but your twice multiple of averaging operator and first central difference operator. This is exactly same as compact discretization with 3 point at x1. This is at x2, and this is the discretization of u double derivative. If c goes to 0, this is nothing but the second central difference operator in the numerator. But this is all happening with the limiting case. So this, in the limiting case, the previous Gauss and inverse quadratic are basically same, and it is not only same, it is same as the usual classical compact discretization. All right. Now, exactly, I am going to define two operators here, fx and sx, one for first derivative, another for second derivative, and we'll write it like this. Next, we'll write u prime at x naught in terms of our operator uppercase f, curly uppercase f, and u double derivative in terms of the operator s. So here this equation I have only written here up to order h square. In here also I have written order h square, but while deriving a high order scheme, you have to take this derivation up to order h6, or rather up to order h8. So this is little bit cumbersome calculation, but only then we will be able to achieve high order approximations. So this is what I have written. These operators fx and sx can be directly applied to solve boundary value problem with second order of accuracy. And these operators uses only 3 neighboring grid points. Thus it is compact and offer tri-diagonal Jacobian iteration matrix, and it can be inserted in a memory efficient manner. So when we apply these operators to this problem, I will get this one. This is basically the system of equation. We will incorporate the boundary values. We will have two cases, one for linear, another for non-linear. Linear can be solved in a Gauss-Seidel manner. Non-linear can be solved in a Newton's-Raphson method manner. That's all. Now, this is fourth order method. I am stopping here, but tomorrow, tomorrow is my, I think, last class. Harindri ma'am, are you here? Yeah. So
Yes, sir. It's your last class tomorrow.
yeah, tomorrow. So I would like to know from the audience. This is one tool, radial basis function. There is one another tool that is called fuzzy method. So these are the two methods that I learned during this lockdown, and and I wanted to share it with you. So it's up to you. If you wish, either I continue with this radial basis function, or I think all of you are having idea of this radial basis function. And there is one more interesting technique, that is fuzzy method. So if you wish, tomorrow I can discuss any one of them, either fuzzy or radial basis, whatever you wish.